So what we want is the magnetic field from a current carrying wire forms a circular arc. Okay. And so the way they usually draw these so here's the wire. It's going to come in and it's going to move along this circular arc through some amount of angle, and it's going to head back out. Okay. And so then what I'll do is I'll have the current come in this way, over that way, and then back out that way. Okay? And then what we can do is we can evaluate this magnetic field here at the center of the arc. So this is going to be our, our point. It's going to be here. And so then what we're going to see is that for a circular arc, they say that this of radius A, like so. If we go and we look at our Biot-Savart law, so this is the mu naught I on 4 pi integral ds cross r hat over r squared. That one right there. Then on these straight line segments, then what we get is when we look at our little ds vector element, when we look at that ds, and then I go in and say, oh yeah, then I need the r. Notice that ds and r are what? They're in the same direction. They're parallel. When you cross them, what are we going to get? Well, actually, the angle between the two when you put them tail to tail is what? 0. Sine of 0 is what? Yeah, you can get anything. There is no magnetic field from that wire. There isn't one from this one either. So those don't count. Only the little arcy piece is going to count. There's a little ds. There's our r. Again, those are 180. Those are anti-parallel. So when you try to cross them, then you're going to get 0 again. The angle would be 180 in that case. So the only one that actually contributes is this piece along the little arc itself. So there's the ds. There's the r. Now these are perpendicular. And therefore, our hat goes like that. Okay? Now this one's going to be really nice. Okay? So when I do the cross product, and we take a look at this ds vector crossed into the r hat, it again goes into the page. So the little differential element of the magnetic field vector, the dB, goes into the page. And it's the same all along the arc. So that's good. I don't need to do any component work. That's what we like to see. And when we go in to find that the B will be our mu naught I over 4 pi And then what we do is we're going to evaluate this cross product. This will be our ds. And then again, the magnitude of r hat is just 1. And then I'm going to have that this is the sine of 90 degrees because they're perpendicular over r squared. This is 1. This is 1. R is A. And at all points around the arc, it's the same. So it's constant. So we're going to pull it out of the integral. So then B, and so this is, I'll do it this way. I don't want to add in the direction. It's into the page. I mean, it's not too bad. So then I can pull out that a squared, and we're left integrating ds. This is like my favorite integral because it's s. It is the arc. All right. And so then what they'll do is they'll go in and state that we incepted some angle. The book called it theta. For the moment, I'm going to call it phi. Okay? Okay. And then what we can do is S is just our arc length of the wire. And so with S equal R phi, or in this case A phi, those reduce. Okay. And again, the book used theta, but I thought that was not so great because the theta comes from the cross product, and so I didn't want the thetas to get mixed up. So I called it phi, but the book uses theta. And so then what you can do is if you go all the way around, we can get that for circle, phi is 2 pi. Then our B would be mu naught I. 2 pi divided by 4 pi is 2 times A, which is the radius of the circle. And for n loops, you just multiply by n. If that n turns on a flat circle, get mu naught ni times 2a, or n times mu naught I, or I don't care how you want to write it. It's all the same. Oh, one thing that is important. Because this has to be in radians. And it has to be in radians because we took it out of the arc length formula. If you want it in degrees, you're going to need a conversion factor in there. You're going to need the pi over 180 factor to go along. And so they don't usually do that. You usually just treat that all angles and expressions probably should be in radians, especially if they're not inside a trig function. So it's kind of like the standard angle that is used in SI kind of stuff. I mean, which is funny because it's not really a unit, but it is kind of the convention type of idea. Okay.